Again, thank you for attending. This is our third seminar in a series that are listed here. For those of you who couldn't make it last time, we are recording this series, and the other series could be found and will be available in the upcoming week on the WPTO's R&D webinar series webpage. And so if you missed a recording, feel free to visit this website here. But today we're going to be focusing on leveraging the advantages of additive manufacturing to produce advanced composite structures for marine energy systems. Also, our last installment in this series is going to be held next week. We hope you guys can join us for our Marine Energy Composites in Manufacturing workshop, which will be held from 10 to 2 next Friday, Pacific Eastern Time. Paul, next slide, please. And just to give you guys an overview and where we're at with this particular project, the project and the R&D that has been shown has been part of our MHK program strategic approaches. This includes some data sharing analysis and also the research that's been conducted for these seminars really fall under the line of the foundational and cross-cutting R&D. Next slide, please. And just to give you a brief overview of where those fall, part of our program is to understand how the environmental and loading effects are on composite materials and to also provide industry guidance for future work. We're doing a lot of work in trying to understand our experimental designs and making sure those fit into the marine energy conditions that are required and are very different from the shipping industry. We're also exploring new standardization methods for our biofouling and characterization methods. And finally, we've done a lot of work to try to evaluate composite performance in seawater and simulated seawater conditions, looking at those environmental effects and really trying to see how these could eventually fit into the IEC technical specification and Wave Energy Scotland types of specification requirements. So with that, I'm just going to go ahead and stop here. I would like to now go in to introduce our next speaker, Paul Murdy. Paul is excited to introduce him. He's been working a lot on a lot of different things with us. He's a postdoctoral researcher in the manufacturing and characterization group at NREL's Flatirons campus. He's been focused on understanding composites materials for renewable energy, and as actually a graduate of Montana State University, from Professor David Miller's group, where he actually studied structural health monitoring techniques and environmental effects on marine energy composites, which was some of the work that we saw last week. Today, he's going to tell you about some of the new techniques and methods that he's doing to help with both wind and water power structures. So Paul, without further ado, I'd like to go ahead and kick off the seminar. Thank you, Paul.
Okay, thank you, Bernie. Thank you for the introduction. Yes, I'm Paul Murdy, a postdoc at NREL in the Manufacturing and Characterization Group. And today I'm going to be talking about some of the seed project work that we've been doing, looking at how we can leverage additive manufacturing to help produce some more advanced composite structures for marine energy systems. So, as Bernie said, I've spent my academic career working in composite structures, and this is just a look at some of the composite capabilities we have at NREL's Flatirons campus in the manufacturing and validation group. So our manufacturing facility is the COMET, the Composites Manufacturing Education Technology Center, where we can do all kinds of composite materials manufacturing research from small scale through to full scale structures. And of course, within the group, we also have the capabilities to validate those structures all the way from coupon scale characterization through to details and subcomponents, all the way up to full scale validation. And that is not just limited to wind blade structures. We can interrogate any kind of structure and their loading. So to break down today's webinar, I'm going to give a brief overview of currently how composite materials are being used in the marine energy industry, and how additive manufacturing might fit into that picture, and how we came up with the goals for this small seed project. So what we really want to do is start looking at how we can integrate additive manufacturing into the overall design and manufacturing process. Based on what we learned from that, we developed two case studies. Case study one is a tidal turbine blade section. We wanted to look at an internal molding approach with additive manufacturing to see what benefits that might offer the design and manufacturing process. And case study two was a much shorter case study, just a very quick design study on a additively manufactured tooling approach to a river turbine T-joint section. And all together, tying all that together to potential future opportunities and challenges that we might see with additive manufacturing in the marine energy environment. So I'm sure everyone on this knows that the marine energy industry is seeing some rapid development right now. We're seeing a lot of different machines go in the water at the moment, and also a very, very broad variety of system designs. As you can see, we have ORPC's cross-flow river turbine, and Verdant's axial flow turbine, just as two examples. Two very different designs that both serve similar purposes, and both utilize composite materials to some degree. Composite materials in this industry is quite an attractive choice for structural components, generally because of their low cost and good environmental resistance. But also, what we're seeing is the marine energy industry has taken a lot of influence from wind turbine manufacturers and boat building as well. So one of the things we've seen is that mold costs for composite structures and tooling costs can be quite a significant barrier to the implementation of composite materials into these structures, especially with a lot of small companies out there that are still in prototyping phases and trying to get their machines in the water as quickly as possible. We kind of pinpointed that there's maybe a need for more cost-effective, low volume manufacturing tooling options for these types of composite structures. And we thought that advances in additive manufacturing could potentially fill this gap. So additive manufacturing, it's not a young industry anymore, and it's still continued to rapidly expand. It started out as just a rapid prototyping technique for expensive, small-scale novelty items, but that's much more turning into a more viable and affordable form of manufacturing. We're seeing a lot of research now for using additive manufacturing to produce large-scale structures, particularly applicable to marine energy. And it's becoming much more close to economic feasibility for mass-produced end-use parts as well. So a few of the most common technologies out there: fused deposition modeling, probably the one most people know. Here's a photo of one of our newer desktop printers in action, the Mark Forged printer, which can also print continuous carbon fiber filaments. Stereolithography, powder bed fusion, binder jetting, I'm probably going to touch on today for printing of metallic structures and ceramic sands, and selective laser sintering as well is pretty common in aerospace. So thinking about how additive manufacturing is being implemented in the composites industry today, It's mainly for external molds for small components. A lot of people who, in their shed, maybe want to make some composite components, can easily print off their molds on a desktop printer and go from there. But we're seeing it in industry too. We're seeing from Oak Ridge, they printed these large-scale wind turbine blade molds through their big area additive manufacturing process. And this is one of the pair of molds that is currently in the current facility. And we're also seeing it for soluble internal molds as well. There's a few printing companies out there that are developing new materials that can be dissolved when a composite mold becomes trapped in the part after curing. As I mentioned with our Mark Forge, continuous filament printing is becoming a pretty significant thing now. Still only really viable on a small scale, but I'm looking forward to when that can be scaled up to something the size of these Oak Ridge blade molds. But ultimately, the main benefits we're seeing with this is that it offers much more increased automation, the potential to reduce a lot of waste, especially in these large molds, and it allows for quicker concept to production, and also the potential for on-site manufacturing as well. Transport costs for large structures, whether it's a wind turbine blade or a tidal turbine blade or whatever, can be quite expensive to transport from a manufacturing facility. So if you can print the mold and manufacture your components on site, there is potential to save a lot of money there. So to take a deeper look at just the mold manufacturing process and how traditional processes compare to new additive approaches. We've taken the traditional mold manufacturing process from wind turbine blades because it's an established industry, and it's not going to see significant innovation as it stands right now, I think. So to manufacture a traditional blade mold, you generally produce a plug. So structural foam bonded together that is then CNC machined down to your final blade shape. And that kind of acts as your master. And that usually needs some preparation, sanding, finishing to prepare it so that you can make your splash mold from the plug. So you lay up your fiberglass or whatever molding material you're going to use on the plug to produce half of your mold. And with the traditional female tooling approach, you'll generally make a blade in 2 different shells and then bond them together. So you'll need 2 separate molds to be taken from the plug. Generally, you'll need a lot of support structure around it to support your splash molds. And then a lot of finishing. You generally need a lot of finishing and sanding on these molds and some chemical treatment to prevent your composite components from sticking to it. So the additive approach, on the other hand, is significantly simplified. It's much more hands-off. You can take your cat bottle, do all the pre-processing, slicing, convert it to G-code, and then go straight to your printer and leave that to print, whether it's in sections or as a single piece. Sometimes you'll need some post-print machining. Oftentimes with the FDM type processes, we'll print slightly larger and then machine down the final tolerance to get a good surface finish. And then similar kind of sealing and finishing of the mold surface. So based on all of that I've just explained, this was a sealing project funded by the Department of Energy's Water Power Technologies Office. And we wanted to use this project to explore the current applications in additive manufacturing for composite manufacturing, and then use that to investigate potential for additive manufacturing in the marine energy industry. And another kind of novel thing that we wanted to explore was the potential for a hybrid additive composite manufacturing process. So could you additively manufacture a mold that would be used for the composites processing, but also stand as a final portion of a load-bearing structure for like a hybrid structural approach, and explore the potential for unique design features from that approach. One of the benefits of additive manufacturing is it offers a much more creative design space. I'm very much a kind of learn by doing type person. So we wanted to take a hands-on approach to some of that as well, come up with some conceptual designs, and then try and produce a reduced scale component utilizing some of these techniques that we've investigated. And then use that as kind of a stepping stone to evaluate some of the benefits of any design features we came up with, and the processes and areas for future development. So to integrate these ideas into marine energy systems, we used the Department of Energy's reference model project as a stepping stone. So the reference model project was a multi-lab collaboration between Sandia National Lab, NRAL, Pacific Northwest National Lab, and a few other partners to go through the whole process for a bunch of different marine energy machines. So a broad variety of machines. And it was more to look at site-specific conditions through to loading analysis, through to structural design, and all the way to cost analysis. Just to kind of outline and define the process. So we used these designs to identify components that would benefit from composite materials, number one, such as tidal turbine blades, nacelles, river turbine blades, maybe the point on a wave absorber, and maybe some fairings on an ocean current turbine, and even fan blades within an oscillating water column. And we used that list to kind of down select to some composite components that could benefit from additively manufactured tooling in particular. So this is how we came up with our two case studies. The additive composite manufactured hybrid structure tidal turbine blade, taken from reference model 1, and the cross-flow river turbine strut T-joint, looking at a soluble tool from reference model 2. So two different internal tooling approaches. So jumping right into case study 1. As I said, additive manufacturing offers a much more creative design space when compared to subtractive approaches. So we look to maybe try and redesign a tidal turbine blade taken from reference model 1, which is a 9-meter blade. And we wanted to design it with an internal additively manufactured mold with a composite overlay on the outside to produce this hybrid structure. And because this approach isn't often taken, I can't find many examples, but we chose this because we thought there were in particular, a lot of kind of unique design and manufacturing possibilities there. So we wanted to come up with this conceptual design and then manufacture a slightly reduced scale blade model to kind of understand it a little bit more and highlight some of the beneficial features. So kind of looking at what we hypothesized, taking a traditional structural manufacturing approach to a tidal turbine blade and comparing it what we thought might be possible with this internal tooling approach. To traditionally manufacture a tidal turbine blade, you would have to do your mold prep. Material can produce some kind of preforms, whether they're in the molds or outside, like shear webs and spar caps. You do your component manufacturing generally through vacuum-assisted resin infusions. Generally have to do multiple skin layups. Like I said, you typically make at least 2 halves and bond them together with adhesives. And then there's quite significant secondary tooling steps as well. Trimming of the root, facing it off, drilling and bonding fasteners within the root so you can attach to the hub. And then still surface finish and grinding as well to get your final hydrodynamic surface. So compare that to our kind of hypothesized additive manufacturing approach. And we foresaw that you could, if you've got your mold printed already, you got to account for the fact that it will be, since it's a hybrid approach, it will be 1 mold per blade. But you have to still prep that mold, do your material cut-in. The structural component manufacturing, we thought it may be possible to just do a single, manufacture the blade as a single component. After the mold has been assembled, and just do the layup of the entire structure as one, and do a single shot infusion. Post-processing, we figured there's a lot of people right now doing some I guess cutting out some secondary tooling with fixturing within the additive manufacturing within their prints. So we figured we could embed fasteners within the composite structure without having to do any secondary drilling or bonding and stuff like that. And then still the same surface grinding finish at the end. So the conceptual design, we came up with quite a few features that we wanted to integrate into a single design. Number one, a disclaimer here is this is not an optimized hydrodynamic or structural design. We kind of simplified it somewhat to showcase some of the manufacturing possibilities first. But despite that, the overall structure was designed to be representative of the final blade structure. So when it comes down to the composite overlay, we still designed it with a thick root buildup. It still has a shear web and some degree of spark cap buildup as well. So yeah, as I said, internal mold offers unique design opportunities. Number one, segmented mold construction. So this tool was designed in 4 separate pieces. Mainly so you're not, well, number one, you're not limited by your printer's size to some degree, but also to alleviate transportation as well. 4 separate pieces is much easier to transport than 1 long piece. So yeah, I touched on the composite overlay design a little bit, but it was designed concurrently with the outer shape of the additive manufactured portions to ensure that you could account for the thickness of the composite to leave your final hydrodynamic shape. And with the composite in particular, a particular benefit is a single piece construction. So the overlaid composite can wrap around the entire structure rather than 2 halves bonded together because these kind of structural adhesives are particularly expensive and they can also be a common failure point in these types of structures. So a little bit more detailed look at this and some of the other features we included in here. The in situ root fasteners. Like I said, we wanted to minimize secondary tooling operations. So we designed this kind of fixture so that we could integrate the root fasteners into the main infusion process. So the idea would be you put down half of your root plies, insert the fasteners, and then lay over your second half of root plies on top. It's not as visible in these drawings, but we also wanted to include a slide-in shear web, so a sandwich panel that would slide inside the foil section to be co-infused during the main infusion. So that would just be a foam fiberglass composite panel that is included or kind of fixtured by this 3D print. And one final thing, we haven't seen anyone do it before, but we thought it might be possible and useful to include resin infusion passageways within the mold itself. So the idea is, if you can keep your infusion lines fixed, you don't need to worry about them slipping out of place, and you get good control of your resin flow throughout the process. So these pieces were designed so that resin would flow in through the inside of the root mold, and then through each section, and then out to the surface where your composite plies are, and flow out through your plies to the surface and around this shear web that's fixed in place as well. So that was maybe like a 2 meter long blade section as designed based on reference model 1, and we reduced the scale down to about a 36-inch span with a 12-inch cord for our actual demonstration and manufacturing. So we printed these mold pieces with a Stratasys large-scale printer with an ABS filament print material because it was cheap and we had it on hand. And this picture gives you a much better view of the shear web fixture as well, and how that sandwich panel would slide inside, and then when the mold is assembled, it's held in place with the infusion. So assembling those 3D prints, it was quite a time-consuming process, to be honest. Sealing the molds was tricky. These 3D prints, the FDM 3D prints in particular, they don't hold vacuum particularly well. There's a lot of air gaps with it between the filament layers. So we needed to seal these molds to ensure good vacuum integrity for the composite manufacturing. So what we did to seal was sand all the surfaces down, and then coat each one inside and out with epoxy, just a wet layer of epoxy resin. Leave that to cure and then sand the surface again. We wanted to rough up that surface again just to promote good adhesion of the composite layers that were going to go on top. So that was done to each segment individually. Some portions we couldn't get to, like the infusion lines and the shear web fixture, we couldn't get inside those to seal them up. But it was still held good vacuum integrity. So we bonded the segments together, pre-printed locating holes for these, so we could just use dowel pins and some nylon bushings to line everything up perfectly, and just use light adhesive to hold them all together. So from that point, we moved on to the composite layup of this component. One thing which we've rarely had to do is structural flow media on the mold surface. So this is just the kind of cross-hatched fiberglass fabric with a lot of space in between it to promote resin flow. But that usually goes on top, since we don't often infuse inside out. We use a triaxial glass fabric just to be representative of a blade structure. So here you can see the root buildup. We put down 7 tapered root plies. We could wrap them around and have them meet at different areas around the circumference. So there was no single point of weakness in the structure. insert these cylindrical fasteners. We use cylindrical in this case just because they're easy to get off the shelf. And then 7 root pliers on top of that as well, tapered even further in the transition section. We also did 4 tapered spark cap pliers, top and bottom, and two skin pliers that wrapped around the entire blade structure, so we could have a continuous skin around the leading and trailing edges, and keep those points where the fabric meet up away from critical areas. And then the infusion process itself, we kept with the resin infusion because it is the very low cost approach to manufacturing these types of structures. Yeah, all the sealing and coating of the mold surface we did definitely paid off. We got very good vacuum integrity around the entire part. So we simply just vacuum bagged with a layer of peel ply, and then vacuum lines were along the leading and trailing edges. So the infusion itself, we had the resin lines entering the part at the root side, so that the resin could flow through those passageways along the entire part and then out towards the leading and trailing edges. So as you can see, the final infusion, we got good full wet out everywhere, not a single dry spot, which really I would deem as successful. So here's a look at the final results once we pulled off the vacuum bags and the peel plies. We have another 3D printed mold here just for comparison again. So the finishing work, it did take a little bit of finishing in terms of sanding and grinding to get the final hydrodynamic profile that you see here. But honestly, not that much more than you would typically do for any externally tooled part. So yeah, and that's just because the vacuum bag side of any resin infusion part is probably going to just be a little bit rougher than your mold side. But because of this grinding, we didn't account for it at this time, but in the future, if you're making a final structural part, you'll want to kind of consider that in your final process. You won't want to go grinding down into your spark cap plies. You'll probably want to design your lathe with a couple of extra chop strand mat plies on the surface to be kind of sacrificial in that. But yeah, as you can see from the cross sections, the infusion was successful. You can see how well the plies draped around these inserts. Again, this is not structurally optimized. This kind of waviness is not something you'd want in a structural part, but definitely further design optimization, you can make that a much cleaner layout around your root inserts. Then we can see that the definition in the spar caps, and how well the in situ kind of fixtured shear web infused too. We got full wet out in that internal cavity as well. One thing that we did see is that the internal cavity of the mold, where there's kind of a reduced infill, just to reduce material usage and print times, some of the resin did make it into that area. So we did have a fairly significant resin excess uptake throughout the infusion. So that kind of makes us want to maybe look at some other sealing possibilities or ways that you can seal up these tight internal pieces. So to summarize this case study in the manufacturing, I thought we were fairly successful in the manufacturing of this reduced scale model, and demonstrating this internal tooling approach, and some of the unique design features that might be possible with this as well. As I said, sealing the 3D print was time consuming and not not fully successful in the tight internal cavities, but we think there are a lot of other techniques available out there to solve this problem in a much quicker way. The embedded fasteners definitely simplified the manufacturing process and completely eliminated that secondary tooling as well. Final finishing of the root section was really just as simple as slicing off the end and just sanding down to that final finish. It really took a lot less work than it would be if you had some kind of secondary bonding there. The single piece construction, everything was infused well and connected well to each other. So I think maybe in the future that does have the potential for increased reliability of these types of structures. But one unknown is the composite 3D print interface. We don't really know how well the composite bonded to the mold without fully testing it. But overall, we have published a paper on this in Applied Sciences Journal for a additive manufacturing special edition. So if anyone's more curious about the dirty details of this project, I would definitely go have a read. So the next steps for this one, this is what the case study we spent the most time on. We really want to start looking at the structural optimization of this additive manufacturing approach. Since this mold is going to be permanent in the structure, we want to look at how you can optimize that to reduce materials, but also use it for things like preventing panel buckling and reducing shear stresses around the leading and trailing edge and around the shear web. You may not even need a shear web if you design your 3D print correctly. But that will ultimately lead us to some techno-economic analysis, kind of accounting for those materials and some of the design trade-offs to see where this approach may stand when compared to traditional approaches and the number of components that you need to manufacture. So that'll take some more characterization efforts and sealing and the composite additive interface research. But we also want to start using thermoplastic resin systems, something we've been doing a lot of recently to kind of enhance the recyclability of the overall structure. And ultimately, we'd like to do a full-scale demonstration of this as well. So case study number 2, this is a much quicker one. This is just a very, very short design study. Really just a quick CAD design demonstration and pitching a couple more additive manufacturing approaches and composite manufacturing approaches that don't get as much insight in the wind and water power industries. So this was using reference model 2, which is a vertical axis river turbine, which went through a couple of different designs in the project, from what I read. This was before my time, but we singled in on this blade strut T-joint right here that was designed for the project. And as it stands now, it's really not conducive to composite manufacturing. Maybe better for subtractive manufacturing and CNC milling of a metal or some other material. And we can see how this T-joint also affects the design of the struts and the blades, which were designed to be manufactured from composites. But again, I've got to kind of reiterate that the purpose of the reference model project was not to finalize some optimized design for manufacturing. It was more just to outline the process and determine the materials required for the cost analysis and such. But nevertheless, we redesigned it to suit a more common composite manufacturing approach. So instead of having this internal T-joint, we redesigned it to simply be an external T-joint for the blades and the strut to slide into instead. So we had this idea that instead of having a trap tool like case study 1, we would do a soluble tool design. So as I said, kind of earlier in this presentation, there's a couple of different printing methods which allow for soluble molds. So fused deposition modeling, you can get polymers now which are soluble in some sort of basic solution. So you can make your trapped internal mold, do your composite processing, and then after cure, you can dissolve that tool out and be left with your final hollow structure. And binder jet printing is similar. It's a very fast method of printing, but you can print ceramic sands that are water soluble and make tools in that way too. So we had this idea that you could simply make this T-joint with a internal soluble tool, which you could then kind of use 4-axis filament winding around the outside of it. And then ultimately, once your part is cured, you can dissolve the print out. And then final construction will be you slide in your struts and your blades, and then bond all that together, and you should be left with a pretty strong and reliable T-joint for that kind of design. So something that wasn't part of this project, part of a completely different project that I'm working on, is some techno-economic analysis specifically for soluble tooling. And we found that the additive manufacturing approach can be significantly cheaper compared to traditional methods, which you'd usually subtractive machine your part from a larger ceramic block. So we found that the additive manufacturing approach, especially for low volume manufacturing, can be much cheaper. Generally because it's much more hands-off, the labor costs are much smaller, and there's far less material waste. Especially with FDM, you can really optimize your prints to minimize the amount of material that you need to make your tool. And that journal article is in progress and hopefully will be available within the next few months. So just to wrap this up, I just want to look ahead to future opportunities and challenges with additive manufacturing and composite manufacturing in the marine energy industry. So the pros, definitely this technology has not shown any signs of letting up anytime soon. It just continues to evolve. We're seeing faster and bigger printers. We've seen much more materials development, much better quality materials that are more applicable to structural applications. And those costs are still falling as well. So we're seeing it being much more applicable to end-use products and large structures. We're seeing much more versatility and the possibility of even site-specific devices. So rather than trying to mass manufacture one specific design, it might be cost-effective to design and manufacture components to specific sites and specific operating conditions. But ultimately, especially as a prototyping technique, we're hoping that we can see people using this technology to just get their machines in the water faster, so they can refine their designs and their concepts, and get to final products much quicker. But to do that, we're going to need to look into a couple of things. We need better understanding of the environmental effects on print materials. If you're talking about metallic printing, corrosion, I think is fairly unknown in that realm. If anyone listening was able to listen into Francisco Moreno's presentation on corrosion, and the same with water absorption in polymers and 3D printed polymers as well. Same kind of deal if anyone was listening into David Miller's presentation. I think there needs to be a lot more work there if we want to see additively manufactured structures in the water. And just, yeah, overall characterization of these materials and a better understanding of how they might react in such conditions. You know, but ultimately my favorite thing about this is being able to continue to explore a much more versatile and creative design space. I think it offers a lot of design opportunities that many other manufacturing processes don't. So thank you all. Thank you all for joining today and listening. Yeah, open to questions now if anyone has any specifically about the case studies or just additively manufactured tooling in general.
Thank you, Paul. That was a great seminar. Thank you so much for sharing this information with us. So it looks like we have our first question. The first question is, how much is the cost for building the parts?
That is a good question. We didn't do any extensive techno-economic analysis at this point because I kind of foresee it as being a much more holistic design approach. We only touched on the design for manufacturing and not the structural design yet. But we did some brief cost analysis. Well, actually touch on a couple of things. Cost analysis for external 3D printed molds. I believe Oak Ridge did some cost analysis there and found that it was a lot cheaper to 3D print these molds. But on a mass manufacturing wind turbine blade scale, it wasn't that influential because a wind turbine blade in a factory is expected to make at least 1,000 parts. But definitely a lot cheaper for low volume manufacturing. From our conceptual design, we did some brief stuff, and we kind of figured it was maybe about 20% of the cost for one component. But with a hybrid approach, you have one mold per component that you make versus a mold that you can pull many components off of. So we really need to look deeper into the optimization of that and see where the crossover might be.
Thank you. I have a question for you, kind of along the same lines, but when you were showing this portion where you were starting to infuse that resin in around the mold, how much time was that in comparison to a traditional, process?
Well, I would say, I mean, half the time, I guess. Because often when you make a kind of blade skin or just half a blade, for simplicity, you'll infuse kind of from the middle outwards oftentimes. Whereas, you know, we were able to do both skins at once. So yeah, cut the infusion time in half. But you know, in a manufacturing environment, they're sometimes doing both of those things at once.
Let's see. There's also another question. It says, thank you, Paul. Really good presentation. What was the surface finish of the 3D printed part, and how relevant is a good surface finish for the final product?
Of the 3D printed part, straight off the printer, I don't know if anyone's played with FDM much, but yeah, it is kind of like a corduroy finish, I guess. You know, which on a small scale printer is not too bad. We did do just a bit of sanding just to rough it up because although it's kind of corduroy, it's still shiny and nothing sticks to it too well. But on a larger scale, like with Oak Ridge's printing systems and really thick filaments, you do get a much more emphasized kind of effect of that, which is why you kind of oversize your print a little bit and then machine down to a final surface finish. But in the case of that blade, we wanted a good bonding surface, so we wanted to kind of rough it up a little bit with maybe like 80 grit sandpaper.
Okay, and just I think one other question we have for you is, what do you think is the biggest or most surprising lesson learned that you've gotten from your seedling project?
Um, Good question. Mm, I guess I don't know. I think historically, well, throughout my career, I've been heavily involved in characterization of mechanical properties of composite materials. And we did try and do a little bit to kind of test out that adhesive composite interface or the additive composite interface adhesion. We kind of tried to develop the test specimens and test them out. And it's kind of really hard to develop the right coupon geometry to get good data from kind of like a lap shear test or a double lap shear test, while infusing a composite over the top of additively manufactured panel. So that's kind of one little nerdy thing that I found particularly interesting that I'd like to look into more.
Cool. Nerdy is always fun. And Paul, we actually have another question for you. In the first case study, you mentioned exploring the use of thermoplastic matrices for these parts. What are the pros and cons of thermoplastics for this particular application?
Well, so we've been looking at recently. NREL has been looking at some infusible thermoplastic resin systems. So I don't know, anyone who's done vacuum infusions will know that that's a very weird thing to come across, a very unique thing. You typically don't get infusible thermoplastics. Um, but one of the benefits they found in kind of their techno-economic analysis, looking at large scale blade structures, was one, you get a much quicker cure time. I think it's like typically 3 hours versus maybe 5 to 8 for epoxies. And another thing is it just uses a catalyst. It doesn't need any kind of curing or post-curing added heat to it. So in the long run, the reduced energy costs were quite significant in the blade manufacturing process.
And another question for you is, as you integrate these molds into structures, what type of design stress values are you seeing comparing to, say, 500 millipascals for carbon fiber laminate?
That millipascals or
Oh,
megapascals?
sorry, megapascals. Apologize.
Oh, well, I see mil, I see mega. We don't know yet. We haven't done the structural design. It's going to be a trade-off between how much composite you use and how much 3D print you use. I don't. I mean, 3D prints. Most 3D print materials don't have a strength anywhere close to 500 MPa. But and it may not be the 3D print holds the main loads, but they'll definitely be capable of holding buckling loads from the panels and stuff, kind of acting like a sandwich panel, if you will. So often in blade structures, we'll use thick foam or balsa wood core in kind of the fore and aft panels to prevent those large panels from buckling under load. I foresee we could do the same thing with additive manufacturing in the internal mold. I hope that makes kind of deviated, but
Yeah. And then also from another question from the audience is, how do we coordinate research efforts with industry and academia to enhance results and advance material science faster? What do you recommend there?
that's a good question. I think attend next week's workshop would be a great start. I think that there needs to be a lot of dialogue between industry, academia, and national labs as well. I think that the advanced materials project as a whole, the much broader project, that's exactly what we're trying to achieve with that, and bring in knowledge from different academic partners and from industry partners with these kind of webinar series as well, and hope to get some feedback on that end too.
And Paul, did you work with any students on this project that
Yes,
you'd like to give a shout out to?
yeah. Jack Dolson was a summer intern here. He was a recent graduate from Montana State University. Um, I don't know if he's on or if he knew about this, but he did a great job over the summer with COVID and everything. It was a fully remote internship, so he did all the designs and got everything down on paper and came up with the manufacturing plans and everything else. So very much credit to Jack on this.
Also, I'd like to add too that kind of along to your question that you received, Paul, that there's other ways that we could do this. There's a program, there's an FRNF POET from our Water Powers Technologies FOA. That was another mechanism that we could also start looking at for interaction. Well, Paul, I think we've come to our time. I would like to thank you for presenting today and sharing with us everything that you've learned from this program. And I'm so excited to see you progress and learn about other things as you get further along in your the next steps for you. Also like to thank the audience. Thank you so much for attending today's seminar, and we hope you can join us next week for our workshop. Thank you again.
Yeah, thank you. Yeah, thanks, Bernie, and thanks for everyone that attended. Yeah, my email address is at the beginning of this slide deck if anyone has more questions and wants to reach out. Thank you.